I want to start off today by talking about the cities analogy that I used at the very beginning of chapter 1 to talk about the different kinds of numbers that there are. And so you might think of it like this. When you were born, if you were born in Montgomery County, you only knew a couple of towns, maybe the town you were born in. And then as you get older, you realize that there are more cities, there are more towns, the nearby towns like Philadelphia, Harrisburg, State College. Your circle of experience grows to something larger, like in Pennsylvania. And then as you get even older, your circle of experience gets larger and larger. You realize that there are cities outside of Pennsylvania. There are these wonderful cities like New York City, Los Angeles, Seattle, Chicago. And then even you start to travel a little even internationally. Maybe you go to Canada or Mexico. You realize that there's this whole other language that they speak. It could be French, it could be Spanish, and that's a little strange, but that's okay because you realize that that they're out there and they're interesting places, and eventually you get used to them. Well, today what we're going to do is I'm going to totally blow your mind and let you know that there's another category of numbers out there, just like there's another category of cities. Look, there's cities in Europe. The languages might be a little similar, but the culture is way different and the way they do things are just completely out of this world. And so that you realize that if you want to combine your experience in North America and your new experiences in Europe, then you have to realize that there are just a whole earth of cities that we have to account for. So today we're going to do a very similar thing with numbers. I'm going to teach you about some numbers that you might not have ever heard of before. And this happens all the time in the course of civilization. Very early on, we're talking about like the dawn of civilization, people had to basically count their sheep. And they had either 1 or 2 or 3 or 4 or 5 sheep. But then someone's herd got slaughtered and they had no sheep left, so they had to include the number 0 in their counting system. And then after that, I have 5 sheep, but maybe you owe me 3 sheep. So how many sheep do you have? You have less than 0 sheep. You owe sheep. You've got negative numbers of sheep. And then people started quantifying things that were not necessarily sheep, but say like, I don't know, pounds of grain or tons of grain. And so you could have a fractional ton of grain. You could have like 1.3 tons of grain or 5.8 pounds of grain. And so they had to expand their number system to accommodate for these new things that they were thinking about. And then they started trying to calculate things like distances of the hypotenuse of a right triangle. They realized that these lengths were not necessarily rational numbers. They couldn't be expressed as a fraction. The Egyptians they had fractions. They had something that represented 1 over 2 or 1 over 3 or 1 over 5. But you can't actually express many of the distances that you're calculating with a Pythagorean theorem with any kind of a fraction. So we had to come up with more numbers, and we now call them irrational numbers. Same thing with pi. If you're trying to find the area of a circle, you can't do it with a fraction of just rational numbers. You have to include pi. Well, in class, we've been trying to solve quadratic equations. And sometimes you get a quadratic equation like x squared equals -1. And so far we've been saying there have been no real solutions, and that's actually true. There aren't any real solutions. But what if we just called the answer to the equation x squared equals -1, we would just call that, I don't know, I. What would that mean? That would mean that the square root of -1 were equal to I. And I, as we're just going to call right now, is an imaginary number. I for imaginary. And it looks like this. Imaginary numbers are completely outside of the system of real numbers. They are not real numbers. If we define I to be the square root of -1, then, I don't know, let's start playing around with it. Well, 2 times I would be 2 times the square root of -1. 3 times I would be 3 times the square root of -1. I is always going to be just shorthand for square root of -1. And we find that these are actually, they're not real numbers. They don't fall anywhere on the number line. You can't draw a line of length I. You can't have I numbers of sheep. You can't have I pounds of grain. The only usefulness for I is in solving equations. is solving these equations here. There's also some other usefulnesses as well. We'll find them later, especially if you deal with circuitry or engineering. These numbers help you model certain situations, but you never really have volts of electricity. You never have dinosaurs that you have to count. They're not real numbers. They are numbers, but they don't belong on the real number line. And then we start trying to do things like add I plus 1 or I plus 3, and we can't really combine them because they're not like terms, first of all, and we just don't really have any way of expressing that kind of idea. So what we do is we create a larger category of numbers, and we call them complex numbers. And complex is, it is kind of a complex idea, but I hope that just the word complex doesn't scare you away from thinking about these kinds of things. Because 3 and I are not like terms, we can't combine them, so we'll just call them a number itself. 3 plus I is a number. 4 plus 2I is a number. Negative 1 minus 0.5I is a number. And these numbers are part of the largest category of numbers that we have called complex numbers. The 3 plus I example has a real part, that's the 3, and the I part, that's the imaginary part, that's the I. But when you add them together, they form a number that is neither real nor imaginary by itself. So we call that larger category complex. 4 plus 2I, there's a real part, that's the number 4. 2I is the imaginary part, that's what it is. And then when you add them together, you get one full number, 4 plus 2I, and we call that the complex number. Now, most of the numbers that you see in the picture right now are real numbers, and those real numbers are still, because they're real numbers, like 0, 1, 2, 3, 4, 5, negative 2, pi, square root of 10, those numbers are real numbers, and because they're real numbers, they are part of the larger category called complex numbers. Same thing, I is an imaginary number, it's the square root of negative 1, but because it's an imaginary number, it's part of the larger group called the complex numbers. I'm going to head back to the printout now. Okay, so here we are, the complex numbers. Now, the complex numbers are numbers of the format, in general, a plus bi, where a and b are real numbers, and I, it's just a substitute for the square root of negative 1, shorthand for square root of negative 1. So we've got real numbers, for example, the square root of 9. Now you know that the square root of 9, when you take the square root of 9, you get 3. 3 is, as we remember, 3 is a natural number, and because it's a natural number, it's also a whole number. Because it's a whole number, it's also an integer. Because it's an integer, it's also a rational number. Because it's a rational number, it's also a real number. And because 3 is a real number, it's also a complex number. It just belongs to the larger group of complex numbers. Imaginary numbers, like the square root of negative 9, if you wanted to, you could simplify that into the square root of negative 1 times the square root of 9. And because negative 1 times 9 is negative 9. Well, we can take the square root of 9, that's 3, and we can take the square root of negative 1 now. We can just rewrite that as I. And so therefore, the square root of negative 9 is 3i. 3i happens to be an imaginary number. That's fine. And because it's an imaginary number, it's also part of the larger group, complex numbers. So let's express these all in terms of I. We can always factor out the negative 1 if we need to. So we can say that the answer is I square roots of 6. Again, just like previously, we write just for formatting reasons, we write the square root of 6 towards the end. That way we know that the I is not inside the square root of this 6. Here, we do the same thing. We've got negative square roots of negative 1 times the square root of 10, and so therefore it becomes negative I square roots of 10. That's the answer. Square root of negative 4, let's split that up into the square root of negative 1 times the square root of 4. It's the part that we can't do by ourselves, the square root of negative 1. And the part that we can do, it's the square root of 4, so we get 2. 2i. 2 times I. 2i is the answer. the square root of negative 25. Negative square root of negative 25 is this. Square root of 25 times the square root of negative 1. Because negative 1 times 25 is negative 25, and so you get negative 5i is the answer. You might think of this as cheating, like, Mr. Bergman, you can't do that. This is cheating, like it's just coming up with a symbol to represent the thing you can't solve. And you know what? That's exactly right. That's exactly how it was discovered. They came up with a symbol for the thing they couldn't figure it out, and then they just decided, well, what would it look like if we just played with that symbol? And this is what they came up with, and it actually turned out to be pretty revolutionary. Square root of negative 5 times the square root of negative 2. One thing it says in your book, it says, caution, all imaginary numbers must be expressed in terms of I before simplifying. So you might try and multiply negative 5 times negative 2 and get positive 10 and consider that the answer. But what we're going to do is we have to follow this rule, and that is we have to express it in terms of I. So this becomes the negative square root of 1 times positive 5 times negative 1 times the square root of 2. So we get I here times the square root of 5 times I square root of 2. Recombining things a little bit, we get I times I times the square root of 10. And what is I again? It's the square root of negative 1 times the square root of negative 1 times the square root of 10. And if we combine these together, then we get negative 1 times the square root of 10. The answer in this case is going to be negative square root of 10. What we've done here is we've combined the i's together in a way that says I squared is going to equal negative 1. And the reason for doing it this way is because we have lots of rules that govern exactly how real numbers need to work, and so while we're still discovering the way that imaginary numbers work, what we really need to do is just put them off to the side as much as possible. You notice here, we're going to work with all of these by themselves, and the rules for radicals are going to be preserved because we've done these all over to the side. More on that later. Let's do the next one. I had to write in the square root of negative 2, but there it is. And what we're going to do is we're going to rewrite these first. Remember the book's caution, all imaginary numbers must be expressed in terms of I before simplifying. So let's do that first. This we get I times the square root of 22 over I times the square root of 2. Yes, these are allowed to cancel. So we get the square root of 22 over 2, which is the same thing as square root of 11. And that's our answer. Number 7. Let's express this in terms of I before we simplify. We get square root of 21 over square root of 3. That's I times the square root of 7. Because we combine the 21 and the 3 together. They cancel. Number 8. We get the square root of, see, this is I times the square root of 16 plus I times the square root of 9. That's going to be 4i plus 3i, which is 7i. You can combine those like terms. I want you to do number 9. Just pause the video for a moment, and then we'll pick up with number 10. So we get I times the square root of 17 plus 3i, because this is the square root of negative 1 times the square root of 9, and that gives you 3i. And we really can't combine things very much further, except we could factor out an I. Like, we could just say that this is going to be 3 plus the square root of 17i. This is a completely imaginary number, as in it doesn't have a real part, it only has an imaginary part. 3 plus square root of 17. We're not going to combine those because you could if you had a calculator, but we're just going to keep it exact. Alright, so next, check this out. Here's where it gets a little even more trippy. I to the first power, that's just I. I squared, that, remember, I is just shorthand for the square root of negative 1. So if we square that, we get negative 1. Now remember, there's no absolute values necessary here because the square is on the outside and not on the inside. We're first taking the square root of negative 1 and then squaring it. Well, if we do that, then we get negative 1. I to the third, well, that would just be I squared times 1, which we already know I squared, that's negative 1 times I. So I to the third is going to be negative 1. I to the fourth, well, that would just be I squared times I squared. We already know what I squared is, it's negative 1. So negative 1 times negative 1 is positive 1. So every I to the fourth, this is the key part right here, every I to the fourth is going to be equal to positive 1. I to the fifth, that's really I to the fourth times I to the first, that's really 1 times I, which is I. Remember, the biggest key part right here is that I to the fourth always simplifies to 1. I to the sixth, that would be I to the fourth times I squared. We know what I squared is, that's negative 1 from up here. So that would be 1 times negative 1, which is negative 1. Turns out, the powers of I are very cyclical. They go in a cycle. They go I, negative 1, negative I, 1. And then the cycle starts over again. This is I to the fourth, I to the fifth, I to the sixth, I to the seventh, I to the eighth. I to the ninth, I to the 10th, I to the 11th, I to the 12th. So, really what you want to do is if you want to simplify, you've got to figure out how many i's there are, I to the fourths there are, like this. I to the 25th could be rewritten as I to the fourth times I to the fourth times I to the fourth times I to the fourth, dot, 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 dot. And then you're left with an I to the fourth, and eventually you get just an I to the first, because 25 divided by 4 is going to be 6 with a remainder of 1. That remainder of 1 means you have, right there, I to the first. All these evaluate to 1. You get 1 times 1 times 1 times 1 times I to the first, which is I. So the answer really is just I. The most important part of this is trying to figure out what the remainder is when you divide by 4. Because remember, the cycle goes in 4s. I to the 18th, that would be, well, what is 18 divided by 4? 18 divided by 4 is going to be 4 with a remainder of 2. So really, I don't even have to worry about the I to the 4s. All I have to do is say that I to the 18th is going to be the same thing as I squared, which I remember from the cycle is negative 1. That's the answer. I didn't even have to write out the I to the fourths, of which there are 4 of them. There's 4 plus 4 plus 4 plus 4 plus 2 is 18, but these all just evaluate to 1, and you don't need to even worry about them. I to the 31st power, 4 divided by 31 is 7, remainder 3. So therefore I to the 31st is going to be exactly equal to I to the third, which is, as we remember, negative I. It's on the table. Bam. Let's keep going. Here's your audio check. Do you know that Paris is the capital of France? Well, it is, and I've been there. Have you been there? If you've been to Paris, the capital of France, then that's your audio check. Let me know. What I'd like you to do right now is I'd like you to begin 2D1, copy the problem list, and start the first problem. After you do that, I will see you in class.